Works. Okay, guys. So, lecture 3, we are going to do a lot. I will go through basically to this, and so you see what this is going to be. So first off, again, so we have to review some statistical concepts that you need to be familiar with, and also because of your next assignment. So I'm going to set up your next assignment very soon. You're going to look at that later on. We're going to talk about independence. There is basically two types of independence. We're going to look at pairwise independence and mutual independence is not equivalent, as you will see. Then we're going to look at the mean and the variance of sums, how to calculate those. This is something that we're going to need a lot of times. And then we're going to look at the simple linear regression also a little bit, so you see how the simple linear regression would be, because in one of your assignments you need to run a regression. So you need to calculate the regression coefficients related to time series, by the way. So that will be some sort of a time series already. And linear regressions, especially, you know, the ordinary least squares are also applied in time series as well, just as for Penna data or anything else. All right, guys, so we need to review this. Now, regarding pairwise independence, we have two random variables, and they are called independent or pairwise independent, you would say, but you can simply say independent. So if there are just two, you can simply say independent, because that's going to be the same, at least for that. Okay, if the joint distribution function, okay, so the joint cumulative distribution function at point x and y, so you have basically 2 points or two different values that you put into, one for x and one for y, is going to be the product of the marginal distribution function. So again, these are the CDFs, you know, and basically what the joint distribution function is. I mean, we don't have that specifically written that down most of the time, but you need to know what it is. So if you look at the joint distribution function of the two, you're going to get the probability that x is not greater than small x, whereas y is not greater than small y. So this is what the joint distribution function is. So CDFs, you know the term CDF, right? And the marginal distribution functions are accordingly the probability, I mean, for x, at point small x is going to be basically the probability that capital X is not greater than small x, whereas the marginal distribution function of y at point small y is, of course, a probability that the random variable capital Y is not greater than small y. Is it clear, guys? Again, so the issue is with dependency, this is not a very practical one, because most of the time when you look at data, you don't know the joint distribution function from which the data is coming from. So it's not a practical definition, it's more or less a theoretical definition. So most of the time we focus on uncorrelatedness rather than independency. But again, you need to know what independency is, because these two concepts are not be equivalent as well. Okay, so there are problems attached to this. I'm going to address them, one or two. Okay, basically it's not going to be practical. Now, we have mutual independence, because if you have multiple random variables, so you have x1, x2, and so on, xn, and they are said to be independent, you can simply say independent or mutually independent. So sometimes the term mutually is simply dropped. Okay, so this is independent, and sometimes even for pairwise independency, this is also dropped, so you need to know what the context is. So we say that they are just simply independent if they're, again, similar, if they're joint distribution function, which is even more complicated because it's not practical. So you have basically n arguments for that, okay, and for each, basically for one random variable respectively, is going to be equal to the product of their marginal distribution function. So that's basically equivalent to this, but we have multiple ones. Now keep in mind, guys, that pairwise independency does not imply mutual independency. It's the other way around. Mutual independency implies pairwise independency, but they're two not equivalent, okay? I could give you some examples related to this, but I want to start with time series after a while. So basically just, you know, I would skip that part. Maybe we can see some examples here and there during OA, but I'm not going to talk about that, okay? So again, keep that in mind. Mutual independency implies pairwise independency, but not the other way around. So again, these things are defined accordingly, just as basically it were from the previous part. But again, the joint probability, so the joint cumulative distribution function is a big issue, because actually when you look at data, nobody knows what the joint distribution function of the corresponding random variables from which the sample was generated from would be, especially when you have, let's say, a large sample. Okay, who knows basically what the joint CDF of the basically of the data is? Nobody, actually, so most of the time. Anyways, so this is not a straightforward concept in that sense, but you need to know what it is. Now, first off, I will talk about basically mutual versus pairwise independence, just as I mentioned before. If the random variables are mutually independent, or simply say just independent, then they're also pairwisely independent, but not the other way around. So you could not turn it around basically in general. Basically, so pairwise independence does not imply mutual independence in general. However, there are exceptions, but most of the time it's not going to be the case. All right, so you need to know that these two are not equivalent even. So mutual independence is even a stronger concept than pairwise independence. All right, I want to show you that basically regarding the example that we saw last week for the discrete random variables. So we have x, and these are the realizations of x. This is the probability distribution, so we have some sort of a uniform distribution, if you like. And of course, y is being equal to x squared. So if y is equal to x squared, realizations of y are accordingly. So we talked about that. This is the marginal distribution basically of y. So you see of each. And then from that, you could basically also establish a joint distribution of the two. We did this last time, so I'm not going to do it again. These are the realizations basically for which, I mean, if x is equal to -1 and y is equal to -1, y is equal to 0, this cannot be, okay? So basically, because if x is equal to, if y is equal to x squared, then you cannot basically have y being equal to 0 while x is being equal to -1. This is not going to happen. So these events have the probability 0 then, and then you can basically just fill out the gaps. So, and that's what we did last time. So I'm not going to talk about that again. This is how you would establish it. But let's say, suppose that this is just given as you see. All right, so it's not a big issue. We want to see whether the random variables are dependent. Of course they are. But let's say nobody will tell you what the relationship would be. So if you didn't know what the relationship would be, just basically the joint as well as the marginal distributions, how would you establish dependency or / independency? Now the issue is you would need to look at some given pair. So I will look at the probability that x being not greater than 0, and so this comma means and, of course. So this is basically the joint probability, you can say, that y is not being equal to 0 as well. So basically, I will look at this pair and I will check whether this joint probability is equal to the product of the corresponding marginal probabilities. And if basically, I mean, it must be the case for every pair there is. Okay, so if I find one pair for which is not the case, then there is going to be dependency regarding the random variables, okay? So you can see now, how would you basically establish some sort of probability like this from the joint distribution? Simple is you need to identify the corresponding events. If x is not being greater than 0, then it's either -1 or 0 in this example. And if y is not being greater than 0, then it must be equal to 0 because there are no realizations being smaller than 0 in this case. So, and then you would simply just consider the corresponding probabilities and you would need to add them up. So 0 plus 1 by 3 is going to be 1 by 3. So the probability that x is not being greater than 0 and y is not being greater than 0 is simply just 1 by 3. Now, of course, this is equal to the joint distribution function of the two at point 0 and 0. So 0 for x and 0 for y. So I'm not going to write down the joint distribution function explicitly. You can also write it down implicitly regarding this case. So this is it, actually. And then you will look at the probability that x is not being greater than 0. Now for that, you need the marginal distributions. Okay, so there is no distribution for y involved. So you need to check whether, or know what kind of realizations basically are involved. These are -1 and 0. Of course, each has a probability of 1/3. So you need to sum up the two, and you got 2/3 for that. And then for the probability that y is not being greater than 0, you do the same thing. You check what kind of realizations are involved, and then of course you'll see that this is the this is equal to the probability that y is being equal to 0 because there is no realization being smaller than that, as I mentioned before. And then, of course, this event has a probability of 1/3, and you can clearly see that basically this is not going to be equal to the product of the two. Okay, so 1 by 3 is not equal to 2/3 times 1/3. So this is not going to be the case because that is 2/9, of course. So you see that over here. Okay, so this is not equal to basically the product of the corresponding marginal probabilities. And so therefore, since you find one pair, that's enough, okay, to blow it up, right? So if you just find one pair that does not satisfy basically the condition, you can simply conclude that the random variables are dependent. Now, just because they're dependent, the disadvantages of that, of course, you don't see what the dependency structure would be. Okay, so from the conclusion that you find that the random variables are dependent, which they are, okay, by construction, you cannot basically obtain the dependency structure right away. That's basically also let's say, a disadvantage of this procedure, all right? basically y is being equal to x squared because I told you so, you know, so that was basically given. But anyway, so you can basically recognize dependency just by looking at joint probabilities versus marginal probabilities, basically for the cumulative distribution functions. Anyway, we're going to look at the further concept. So what if basically they are dependent? So let's say if they are dependent, in this case pairwisely, because you just got two of them, okay, then the densities, the joint density as well as the joint probability mass functions are going to be similar. All right, so again, in this case, the joint density or slash the joint probability mass function is going to be equal to the product of the marginal densities or slash the marginal distribution, marginal probability functions, basically for continuous or slash discrete random variables. So if the random variables that are involved are discrete, all right, so both of them, and I'll only look at that case, so either both of them are discrete or both of them are continuous. I mean, you can also have the case where one is discrete and the other one is continuous, but simply just ignore that, okay, because usually they have kind of some sort of similar distribution. So if both are discrete, then they're independent if and only if, so that is also basically being equivalent, the joint probability mass function is equal to the corresponding product of the marginal probabilities. And this is basically what it is if they are continuous, but then you would simply need to replace the probability mass functions by the corresponding densities. So that's basically how you do it. All right, is it clear? So in this notation, guys, you need to know this from the context, okay, whether this is a density function or basically the probability mass function, just like the other. And you would need to find it out basically looking at the random variables. Again, I only consider the case where both are discrete or both are continuous, and with the density, of course. So if they are continuous, they have, in this case, they have a density function, respectively. Is it all right? Okay, so this is something that you could also do. Now, going back to this example, basically the previous one, okay, or maybe I'm going to look at that later on. I'm going to define another thing which is going to be important here in this context. So this refers to basically multiple random variables in general, and they're said to be basically of the same or identical distribution. So if I say identical distribution, I don't mean the uniform distribution, guys. So they can have the uniform distribution respectively, but that's not the case in general. So they have identical distributions, okay, if their corresponding cumulative distribution functions are equal. So if the cumulative distribution function of the random variable x is also equal to the cumulative, x1 is also equal to the cumulative distribution function of basically of x. Now, not at the basically at the different points, but at the same point. There is an error on this slide. I will need to fix it, but please ignore this for a moment, okay? So the argument would be the same. So if you put basically x into the cumulative distribution function of the first random variable, you would find that the result must be the same as if you would put x into basically every other cumulative distribution function of every other random variable in this case. So if they have the same distribution, then of course they have the same cumulative distribution functions. That's the definition basically, by the way. Because the cumulative distribution function is one of the most important concepts regarding random variables or regarding the characterizations. Okay, if you know what the cumulative distribution function of a random variable is, then you absolutely know everything about the random variable. Okay, whether it's discrete or continuous, whether it has a density or not, what's the basically expectation, what's the variance, and so on. So you can basically get that, and this is what the common denominator is for all random variables. And if the cumulative distribution functions are equal for every random variable there is, okay, then they have the same distribution, period. Or you can simply say identical distribution. But I apologize, again, so there is an error on this slide. So the arguments must be the same. Okay, so please ignore this for a moment. I will fix it when you, basically when you, I update the slides so to this lecture. All right, now please ignore this for a moment. So if basically in addition to this, not just basically that having the same distribution, all right, so they have identical distributions. If in addition, they're also independent, okay, not just having the same distribution, but they're also independent, so both, okay? So this means they are identical and independently distributed. So we simply express this by using the acronym i.i.d. i.i.d. stands for independent and identically distributed, or you can also say independently and identically distributed. Okay, but we would say independent, so they are independent and identically distributed. This is basically what it stands for. All right, is it clear? You might heard the term i.i.d. Okay, so again, i.i.d. means that they are dependent, but not just dependent, they also have the same distribution. That's it. Okay, so if they have the same distribution, then basically their cumulative distribution functions are equal. Is it clear? All right, so that's basically what it is. Now, if basically they are i.i.d., okay, and then of course not just that, but if they are having just the same distribution, then their moments are the same. So if the expectations are finite, the expectations of each are going to be identical. That's something that you need to understand. So the expectation of the first is going to be the expectation of the second, because, and then if they have the same distribution, they also have the same parameters of the distributions. Okay, so this is also the same conclusion. So then the mean and the variances also, okay, are going to be the same. Now, this is also not true in general if you reverse it. So just because random variables have the same expectations and the same variances, respectively, it doesn't basically imply that they also have the same distributions in general. So that's basically true. All right, so they can have basically, one can be basically binomial and the other one can be normal, can have basically the same expectations and variances, but you could not say that they have the same distributions. But they have the same distributions. They also have the same moments, let's say. If they have the same moments, then basically they have the same expectations and variances. Is it clear, guys? So let's say if there are i.i.d., and then of course, and let's say if the expectation is, let's say, mu of each, and the variance of each is, let's say, sigma squared, not necessarily normal, guys. So sometimes basically this is, you know, this is called conditioning in psychology. So anytime people say mu and sigma squared, they think about the normal distribution. That's not necessarily true, guys. Okay, so you're not supposed to. Okay, but if basically this means that if each has the same expectation, each has the same variance, okay, and they have basically identical distributions and they're independent, then we simply just write, okay, that they are i.i.d. with mean mu and variance sigma squared. But again, keep in mind, not necessarily normal. So they can be normal, but this is not true in general. Got that, guys? Is it clear? So as far as basically this is concerned, right? So you need to basically know this. This is just a notation that you're going to see. We're going to namely assume that error terms regarding a time series, for example, for different type of processes, namely AR processes, so autoregressive processes and moving average processes, are going to be i.i.d. with mean 0 and a constant variance. All right, so you'll see basically, this is the easiest case though. And yeah, there are also basically errors where they are not i.i.d., but I'm going to keep it simple, at least at the beginning. Now, we're going to look at the continuous case, though we haven't seen a continuous example. And as you see, it's going to be a little bit more complicated, so you don't need to write that down. The joint standard normal density of two standard normal random variables. So keep in mind, x and y are both following the standard normal distribution. And then there is a possibility to express the joint density. The joint density is going to be 1 by 2 times pi times the square root of 1 minus rho squared. Now, rho is going to be a parameter. I will talk about that soon. Times e to the power of, and then you have a huge exponent, guys. But you don't need to write that down. So this is going to be negative 1 by 2 times, in parentheses, 1 times rho squared times, and then you have a huge expression in brackets, x squared minus 2 times rho times x times y plus y squared. Okay, so then this is the joint density again. So even basically, this is the simplest case, by the way, trust me. Okay, so the joint density functions of the normal distribution are, let's say, more or less still humane. Okay, so believe it or not, this is how it will look like. Now, I'm going to address what the parameter rho is. First, I'm going to calculate the covariance of x and y. I'm not going to calculate this, but I'm giving you basic instructions how to. Now, what you would do is basically to calculate the covariance is the expectation of the products, or the product of the two, sorry, minus the product of their expectations. Now, the expectations of each are going to be 0 because they each following the standard normal distribution. You can get that from the density. And how would you calculate basically the expectation of their product? The expectation of the product is done basically by the following integrals: x times the joint density, okay, and then you integrate this with respect to x from minus infinity to plus infinity, and then you also do this, I mean, you would multiply that by y, and you also integrate the whole thing with respect to y, and also from minus infinity to plus infinity. You can do it partially, so first you integrate it with respect to x, and then you would integrate with respect to y. I'm not going to do this because it kind of sucks, okay, so I'm not going to basically elaborate on that, but you will see what this is going to be, so I will skip it, but that's the way to do it, Okay, so we haven't seen this before. I didn't give you an example to that regarding expectation of a products, but you might remember for calculating expectation of products, you would have the joint density of the random variables or the joint distribution, let's say in general. I mean, if they are discrete, then of course you would use the joint probability mass function, but if they're continuous, you would use the joint density function if they have the density, and then minus 0 times 0, which is basically the corresponding to the product of the expectations. Yes?
So this equation is true when x and y, they are independent in the identically.
Not just then. So again, basically this is always true, no matter what. So basically the covariance is always like this. And in case of if they have the joint density, only they're supposed to have, then basically this is what it will be. Okay, so if both are continuous, okay, so and both are continuous with the joint density fxy, okay, then you would basically get the expectation of the products by using this integral. This is basically what we have illustrated last time already. But I only look at the discrete case. I didn't go through that one. Okay, but I wanted to give you that one also as well, so have at least know. Now, I'm going to skip basically calculating integrals. You have enough integrals that I mean, I would give you, the assignment also. Please don't forget that. Okay, so the deadline is going to be next Friday, so you got 2 days left. Okay, I already received one or two solutions. So anyways, so in this case, I will skip that one, but you will find that this is going to be equal to rho. So if you do that, okay, for this density, again, so the reason why I skipped this basically is obvious, okay, because it kind of sucks. But again, it doesn't matter. It's going to be rho. Okay, so that's the result. Okay, again, but you would just need to, you would figure that out after a while, and then you would calculate the correlation basically of the random variables. Correlation is by definition the covariance divided by the product of the standard deviation. So the standard deviation of x, which is the square root of the variance, times the standard deviation of y, which is also the square root of its variance. And then since basically the variances are both equal to 1, because we have the standard normal distribution, of course, this is something that you could also show looking at the densities, integration by parts and this and that. Okay, so I will also have that considered. Then this is going to be equal to the parameter rho. So rho is the correlation, technically speaking, between the two, and this is basically how you capture it. So there is only one parameter here in the joint density, guys. That's not here, that's here. All right, so here it is. Okay, and everything else is going to be clear because the mean is 0 for each and the variance is 1. All right, so this is basically what it is, and you would know that the correlation must be between -1 and 1. And this is also clear here if you look at basically the expression here under the square root 1 minus rho squared. Okay, so if rho is not basically, let's say, less than 1 or basically being greater than -1, so let's say if it is equal to 1, okay, that's not going to happen. So actually, it's not supposed to be 1, but the statement is still true. It doesn't matter. So it must be strictly between -1 and 1. But it doesn't matter, so I will skip it. I will look at that one. Now, anyways, because if you have, and this is what okay, let me show you how the density would look like for different kinds of parameters. So for, let's say, rho being equal to -0.9, this is how it would look. And then I will show you how basically the joint density is looking for different parameters. All right, so again, you don't need to know this. You would not need to get this is what I did basically by using my computer. And yeah, this is just, I wanted to see you to see the joint density of a bivariate standard normal distribution. Anyways, okay, so this is how it would look like. Now, I want to check basically what is happening regarding independence or dependence. Again, I don't know it yet. This is what the density was, and I want to figure it out basically what is going on regarding dependency. So let's say I take the density as it is, and if, let's say, rho is equal to 0, then I simply substitute for 0 regarding the correlation. And if basically this is equal to 0, then this expression becomes just simply 1 by 2 times pi. Okay, so this is a more compact version of it, which is obvious. And then you have e to the power of the whole thing. Now, if you look at that closely, you find that if this is equal to 0, then this is going to get canceled, of course. And then this is not going to appear there anymore as well. So this is simply just 1 by -2 times the sum of the squares. And that's what I'm going to write inside basically the exponent. So e to the power of -1/2 times, in parentheses, x squared plus y squared times 1 by 2 times pi is going to be basically the joint density to which it basically reduces to if this parameter is equal to 0. Now, in this case, you was also going to see, now I'm going to split basically this expression into two parts, okay? So first, this is going to be 1 by the square root of 2 times pi, and times 1 by the square root of 2 times pi is going to be that. So again, I will split it in two parts, okay, or two halves, let's say, and then I'm going to also split the power, or the, I mean, it's not a power function, it's an exponential function, but you have a power now. The base is the Euler's number and the exponent is negative 1/2 times the sum of the squares. And this is something that you can also split, because if you multiply two powers where the base is the same, you simply just add the exponents. So this is going to be equal to e to the power of negative 1/2 times x squared times e to the power of negative 1/2 times y squared, because if you multiply these two, okay, so if you're going backwards, if you multiply these two, again, these are powers, so the base is the same for both, and then you simply just add the exponents. If you add the exponents, you got negative 1/2 times the sum of the squares. This is what it's going to be. All right, so you understand how I'm splitting this basically into two halves. All right, so the first is going to be, of course, the density or the marginal density of x, because this is the marginal density of the standard normal distribution, as you might recognize it, okay? And the other one is going to be the marginal density of y. And as you see, if basically they are uncorrelated, they are also independent. This is a very specific case regarding the normal distribution. So usually it's not true. If they are basically independent, then they are uncorrelated. So that's basically how it goes. But for the normal distribution, you also have that if they are uncorrelated, then they are also independent, by the way. Because the product of the marginal densities equals the joint density, and that's the only case for which this is. All right, is it clear? So this is what it's going to be. Now, they're not just independent, but also since they have the same distribution, they are also i.i.d. So in addition to that, because both are standard normal and they are independent, then they're i.i.d. regarding, or you can also say then normally and identically distributed. So we also use the acronym NID for that. Okay, so NID means normally and independently distributed. Okay, or normal distribution, or normally and independently distributed. Understand what I'm saying, guys? Okay, so in addition to that, but they're i.i.d., so they're independent. All right, now let me summarize this because it might confuse you. If random variables are pairwise independent, so I'm looking at just two, okay, then they're also pairwise uncorrelated. Pairwise uncorrelation, I mean, you can, correlation is only a concept for two, okay, so if you say pairwise uncorrelated, they're uncorrelated, simple as, okay? But if you have basically three of them, so let's say x, y, and z, okay? Pairwise uncorrelatedness means that x and y are uncorrelated, as well as y and z are uncorrelated, as well as x and z are uncorrelated. So if you have multiple random variables, the concept of pairwise uncorrelatedness basically can also be established easily, but you need to look at the combination. So every combination, if you pick two, any two, they must be uncorrelated as well. Is it understandable? So that's why I say pairwisely uncorrelated, although I would not, because correlation is simply just a concept which is only defined for two of them. Anyways, so if they are pairwise independent, meaning that there is no relationship between the two, then there is no linear relationship also. All right, so that makes sense. So uncorrelated, this means there is no linear relationship between the two. And if there is no relationship, then there's also no linear relationship. But just because there is no linear relationship, it doesn't mean that there is no relationship at all. However, for the normal distribution, this is going to be equivalent. So if the random variables are normal, then pairwise uncorrelatedness is going to be equivalent to pairwise independency. All right? Is it clear, guys? So if they're independent, they're also uncorrelated, which is also true, always true, no matter what. But if, for the case of the normal distribution, if they're uncorrelated, then they're going to be independent as well. Okay, so you didn't, I mean, as it was basically demonstrated in the previous part. Okay, if the correlation coefficient was 0, then they would be also basically independent, which is not true in general for, let's say, an arbitrary set of random variables. Does that make sense? Okay, so for the normal distribution, it is true. This makes basically the normal distribution highly practical. So you would only need to look at the uncorrelatedness, because then if you assume that they're normal, then they're also independent. Simple as. All right, so then you can establish independency by just simply assuming that they're normal and check whether they're uncorrelated or not at the 5% level at least. Is this understandable? All right, so you can basically look at that one. Now, regarding expectations of sums, we're going to look at basically expectation of sums also. Okay, so that's simple. Expectation of sums is going to, or expectation of a sum is going to be simply the sum of the expectations. Okay, believe it or not, this is a little bit more difficult to prove than as you might suggest, okay, but it's basically also intuitive, right? So again, this is always true, even if you have multiple random variables. So if you have basically even 3 of them, so expectation of y plus x plus y plus z is going to be expectation of x plus the expectation of y plus the expectation of z then. Is this understandable? Again, so this is basically can be extended by using complete induction, by the way, so if you have a finite number, but it is also true for an infinite number if there's a limit to that. Anyways, okay, so this is something that I want you to remember. I'm going to use this quite frequently, so basically maybe every other lecture you're going to see some expectations of sums and the variance of sums. Now, regarding the variance of sums, in general, if you know nothing about basically uncorrelatedness, you will find that this is the sum of the variances plus 2 times the covariances of the 2. So if there are 2 involved, this is basically how it evolves. All right. Now, I want you to basically to look at that one. If they're uncorrelated, then of course the variance of a sum is going to be the sum of the variances. This is something that you see. So if they're uncorrelated, which means that basically the covariance is 0, then this is what it's going to be degenerating to. But this is not true in general. Now, how would you basically establish that? Because I want to generalize this also for multiple random variables. If you look at the so-called variance covariance matrix of the 2, which is going to be sigma. So sigma, capital sigma is not a sum. Capital sigma is going to be basically matrix. In this case, okay, this is how it would look like. So you would have basically the covariance of the random variable x with itself, which is of course equal to its variance. So if you take the covariance of a random variable of itself and with itself, then this is going to be its variance, but I keep it as is because I want you to understand the structure. Okay, so here, of course, x is going to be replaced by y because let's say this is basically for the rows. So you have the covariance of y and x. And then here on the other side, you have the covariance of x and y because then x is going to be standing for the columns, okay, or look at the column index. This is going to be replaced by y. So this is basically how it will go. And then you have down there the covariance of y with itself, which is equal to its variance. But I keep it as is because in this structure, you can also address how it would be. Okay, so again, this is the variance of x, as you would see. This is the covariance of, the covariance of y with itself is the variance of y, of course. And then you have 2 times the covariance, okay, 1 and 2. So actually, if you look carefully, guys, okay, I want to basically go through this far. The variance of a sum is going to be, as you can see, the sum of the elements from the variance covariance matrix of the 2. Understand that? So that's a mechanism that is, that works here. If you remember that, you can generalize this relatively easily. So the variance of a sum, I will refer to it as such, is going to be the sum of the entries from the variance covariance matrix of the random variables. Yeah, you raise your hand. So.
But there are more variables.
If they have more, then it's going to be similar. So that's what I was basically introduced you to it. So this allows you, if you remember that basically that the sum of the elements taken from the variance covariance matrix is going to be the variance of a sum. You can easily generalize this for multiple ones. And that's what I'm going to do in the next part. So if you have multiple ones, let's say n, and I'm going to look at the finite number. Okay, so because then if the number is not finite, then of course you would not be able to establish the variance covariance matrix, which would be indefinite, of course. So this is something that I can't do in practice, but most of the time it is going to be finite. So again, but anyway, the expectation of a sum is going to be still going to be the sum of the expectations, no matter what. Okay, so you understand? I will basically, so you can bypass the sum operator, guys. So regarding this, I'm going to basically use that frequently. So if I have the expectation of a sum, okay, so let's say you have a sum of, let's say, certain random variables. I'm not basically establishing, the limits of the sum because it doesn't really matter. You can simply just bypass the sum operator, okay, so you can, that's what I'm going to do, is going to be the sum of the corresponding expectations. And that's what you're going to see. All right, so this is basically how I will going to deal with that issue. Is it clear, guys? And then you can say from the first to the last, but it doesn't really matter. Does that make sense? Okay, so I'm going to break in with the expectation operator into a sum by simply just changing the sum operator and the expectation operator, and this is how it's going to work. So you'll see this quite often. Yeah, so I want you to basically to prepare for that. Now, regarding the variance over sum, I'm going to basically say the same thing. This is going to be the sum of the elements from the variance covariance matrix. Check it out. This is how it would look like. So this is the reason why, among others, I don't change that to be the variance of x1, because it is. So if you take the covariance of x1 with itself, this is going to be its variance. But if I change it, you don't understand basically the structure of the variance covariance matrix directly. But if I don't, then you do. Okay, so this is how it will go. So here you have basically the row index, right? So moving from row to row. And then for the other one, you have the column index. And of course, the covariance operator is a symmetric operator, which means that the covariance of, let's say, x1 and xn is going to be identical to the covariance of xn and x1. So what you would do when you have that is you simply take all elements and sum them up, and that's it. And that's what you do, okay? And you can basically easily represent this by looking at the following sum. So I'm basically addressing covariance of xi and xj, xi and xj in general, because most of the time they are different. So the row index is not equal to the column index. But if you want to sum up basically an element of a matrix, you simply put a double sum to it. Okay, so you sum up with respect to the rows, and then you sum up with respect to the columns. Again, I denotes the row index, let's say, and j denotes the column index. And you can say, if you look at that one, this is going to be the covariance in the ith row and the jth column of the variance covariance matrix, and you simply just take this double sum basically with respect to the rows and with respect to the columns, and that's what it's going to be. Do you guys get that? Okay, so whenever basically you look at the random variable or the covariance of a random variable with itself, you simply just replace it by the variance. Because keep in mind, guys, okay, I didn't tell you this, but I think I owe you that one. So if you look at the covariance of a random variable with itself, this is going to be equal to its variance. So you have the sum of the variances plus 2 times the sum of the covariances, because the elements above the main diagonal are identical to the elements below the main diagonal. Keep in mind, guys, that the variance covariance matrix of every random variable, every random variable, so in case you want to establish it, is going to be symmetric. So the variance covariance matrix is always going to be equal to its transpose. Okay, it's a symmetric matrix. You understand? So if a matrix is called symmetric if it's equal to its transpose. So when you do a transposition, you know what transpositions are? You know, so when you replace the rows by the columns, this is what it's going to be. And by definition, we're also going to assume that it's going to be positive definite, which is denoted that like this. It doesn't mean that the entries are always going to be positive, guys. So this means positive definiteness, okay? But regarding positive definiteness, maybe I also am going to find it, but this is not going to basically be important in this course. So it's going to be a symmetric and positive definite matrix. Usually we use the acronym SPD, okay? SPD is not the political party that I'm referring to in this case. SPD is a matrix that is symmetric and positive definite, guys. There is a political party in Germany, I don't know if you heard about it, which is called SPD, but that's not what I'm talking about. You understand what I'm saying? So people kind of accuse me of, you know, conspiracies and stuff. But again, I'm not basically just going to that. So symmetric and positive definite, which is the variance covariance matrix by construction. Anyways, all right, guys. So if but this is not what I'm going to use most of the time. Because in most of the time, you have independency. So if you have basically, let's say, also i.i.d. random variables, but pairwise uncorrelatedness is going to be enough. So if they are pairwise uncorrelated, which there are, if they are i.i.d., okay, so if they're i.i.d., they're also pairwise uncorrelated. And if they're pairwise uncorrelated, then you can basically ignore the covariances. Then the variance of a sum is going to be, because the covariances are 0 if they are different. Okay, so in case they are different, they're going to be 0 covariance. So then, of course, the variance of a sum is going to be the sum of the variances. So I'm going to bypass basically also the variance operator by the sum operator, but if basically I make sure that the random variables that are involved are at least pairwise uncorrelated, which they are if they are also pairwise independent, which they are also if they're mutually independent. So these are stronger concepts, but pairwise uncorrelatedness is going to be enough for that. Is it clear, guys? So you can simply, then the variance covariance matrix, guys, is going to be a diagonal matrix. You know what a diagonal matrix is? Basically, the diagonal matrix is a matrix that has zeros outside of its main diagonal, and the main diagonal will have the variances, right? So this is basically what it will be. All right, so this is basically the most common case that I have, because that's easiest. Understand what I'm saying? But in general, it's not true. Okay, so when it's true, then I simply bypass the sum operator and the variance operator, and this is how it's going to be. Now, let me talk about the simple linear regression model. Let's say you have an index, okay, for observations. So you have 5 observations. You have some x, okay, which is an explanatory variable. We also refer to be that as a predictor. Predictor is not the same thing as the explanatory variable, because the constant of the regression can be also a predictor, whereas this is not an explanatory variable. So explanatory variables and predictors are not synonymous. Sometimes I'm going to use them synonymously. But again, the constant of the regression, you might remember that, can be also regarded as a predictor, but that's basically what it would be. And then you have y, which is the dependent variable. And this is also called a response, and they have some observations basically attached to it. So again, this is what the regression is going to be about. Okay, and then I will calculate basically the regression coefficients, correlations, coefficient determination, stuff like that. So I want to do that. I won't give you an assignment where you would have to do this, okay, regarding time series. This has nothing to do with time series, but I haven't, basically, I want to have them recalled, okay? You'll find a formula in the book, okay? So I call this the script, but it's going to be a book to this course, as well as in my old statistical script, okay, which is in German. So I think it's chapter 4 in my book, and then basically my old statistical script, you have corresponding formulas. Actually, it's not a big deal. You need the arithmetic means, you need the empirical variances, you need the covariance. Maybe you also need the correlation here and there. You need the regression coefficients, which are the slope and the intercept, and then you would also need the coefficient determination at this part. Okay, then you also need the standard error of regression, and then the standard errors of basically of the regression coefficients. So these are going to be basically the issues. I'm not going to that far, so I will stop at the coefficient determination, and then next time I will finish it, because the standard errors are required to do hypothesis testing. So I will do that as well. Anyways, but that's what we're going to do tomorrow. So the arithmetic means are the sum of the observations divided by the number of observations. And since you got 5 of them, basically you sum up the observations as you see, basically as you get them from the samples. So this is something that you would do, okay? And then you divide them by the sample size. If I say division, that confuses people, although it will have a multiplication here involved. I mean, dividing things is going to be the same as multiplying them by its inverse. So if I divide something by 5, it's technically multiplication by its inverse, which is 1 by 5. So if you multiply by 1 by 5, technically this means division by 5. You understand what I'm saying? So don't be confused if I say division and you don't see, you just see the multiplication, because the two are equivalent, guys. Now, the arithmetic mean in this case is 75, if I'm not mistaken. And the arithmetic mean of the other sample, basically, which is the sample of the response, is going to be basically obtained accordingly. So you have the sum of the observations, as you see, divided by the number of observations. So that's that. At least you should know that one. You understand what I'm saying? So if you don't know this, then you have no idea about statistics. Now, anyways, okay, so I keep those, okay, and I'm going to calculate the empirical variances. Keep in mind, I'm not going to correct them. Correction basically means the bias correction regarding estimation. So these things are going to be purely descriptive, not inferential. Inferential statistics, when you try to estimate variances of statistical populations, but that's not what we're going to do. So I'm not going to correct them. So if I basically consider empirical variances, which I denote by S squared, okay, then you will have basically the mean of the squares minus the square of the mean, or the mean of the squared deviations of each observation to the arithmetic mean, either of the two. I'm going to stick to basically the other one. So the mean of the squares minus the square of the mean is going to be basically, I mean, you take the sum of the squares, so 60 squared plus 70 squared plus 75 squared, you know, and so on. So this is going to be from here to there to this part. This is the sum of the squares, right? Divided by the number of observations yielding the mean of the squares. So what you see here, and this might be good to know, okay, I'm going to give you that one. As you might see, this is from here to this part, this is the mean of the squares, okay, and then you have minus the square of the mean on the basically if you continue, minus 75 squared. So this is the square basically of the mean, and they are not identical in general, okay? If every observation is the same, they are equal, okay? But most of the time they're not, because if every observation is the same, there is no variance, or the variance is going to be 0 then. Do you guys get that? Okay, mean of the squares minus the square of the mean. Again, in theoretical considerations, the variance, this is not the empirical one, guys. So there is basically 3 types. Okay, this is the empirical one. This is the theoretical one. Don't use the variance operator basically for empirical considerations, okay, because that involves random variables. Okay, so this is the expectation of the square minus the square of the expectation. Similarly, okay, you might remember that one. We used this quite frequently last week. All right, that's not the same thing. So keep in mind, guys, the arithmetic mean is not equal to the expectation. The arithmetic mean is just an estimation, basically, for the expectation. This is inferential statistics, by the way, so don't confuse the two, okay? If you do, then I'm basically going to penalize that regarding your assignments, okay? So not supposed to. You're going to distinguish, I mean, you have to distinguish between empirical and theoretical concepts, all right? Of course, empirical variance is the empirical counterpart of its theoretical version, all right? But this is it. Now, I got 100 here, if I'm not mistaken, so mean of the squares minus the square of the mean is that, and then you also have basically the same mechanism here applied for the other sample, basically for the sample of the response. Mean of the squares involves the sum of the squares, which I'm basically representing here, and then divided by 5, which is yielding the mean of the squares minus the square of the mean. This is going to be basically the empirical uncorrected variance. So uncorrected means, okay, that I'm not going to consider basically its estimation, because you might know this, all right? So you might remember that the expectation of this estimator is not equal to the variance of each random variable respectively. Okay, so that's the issue where this is involved. I'm going to address inferential statistics next time, but not this time, because again, I don't want to do inferential statistics now. I don't want to basically just do descriptive ones. All right. Now I'm going to continue. So I'm collecting those results, and I'm going to address the empirical covariance. You might remember the theoretical covariance. The theoretical covariance where random variables were involved was equal to the expectation of the product of the two minus the product of the expectation. Keep in mind, guys, this is a purely theoretical issue. So for the expectation of the product, you would need to have the joint distributions, all right? But here I don't need to have the joint distributions. I just have sample observations here. So accordingly, this is going to be the mean of their products, okay? So you have basically the mean of their products. So 60 times 2 is a product, right? And then you calculate this accordingly, 70 times 3. Then you have 75 times 5. You have 80 times 3. And then you have 90 times 5 again. So one observation from the sample of the predictor and one observation from the response. You understand that, guys? Okay, so that's basically it. You take the mean of the products. This is the sum of the products, all right? So again, if I basically explain this, this is the mean, the red one, mean of products, all right? Okay? And then you have the other one, which is the product of the means, all right? So the other one is the product of the means, all right? So what's the difference basically between the two? Similar to the variance. For the mean of the products, you need to have the products first, and then you take the mean of those. Whereas for the product of the means, you take the mean of each sample first, and then you multiply them, and then you'll have basically the product of that. Is it clear, guys? Okay, so that's not going to be the same in general, of course, all right? Because if it's the same, then the covariance, empirical one, is going to be 0. There is no correction here involved, anything, so this is what it's going to be like. Okay, and I got 9, so this means that, of course, it's greater than 0, so we have a positive trend in the data. Now, you're not supposed to say that if X increases, then Y increases. So it's important to say that if X increases, okay, all right, so this is basically important, then Y tends to increase as well. Okay, so that's very, very important. So Y tends to, okay? I'm not saying it does, okay? So just because X increases, then it doesn't really matter. That doesn't really imply that Y does the same. Okay, but it tends to. Okay, so I'm like, okay, so when I read papers and stuff from students, okay, and the people say something like, you know, if X increases, then Y also would increase, right? And then I would say, okay, just because I'm tall, it doesn't mean that I'm fat. You understand what I'm saying? So you need to basically be very careful for this. Okay, all right. So please express yourself accordingly. It only tends to be. right, the case, but that's not necessarily true. All right? Okay, as you might know, tall people tend to weigh more than small ones. Okay, but it's not necessarily true for everybody. Okay, so just because you're tall, it doesn't mean that you weigh a lot. Is it clear? All right. Okay, so that's my comment sometimes, and then students ask me what it is about, and then I would respond, okay, just think. Anyways, okay, guys, so that's that. Okay, regarding the covariance, it's 9. So again, the number 9 doesn't tell us much, to be honest. Okay, so there's not much information involved other than it's positive, okay? Because you need to basically to calculate the relative covariance, which is going to be the correlation. So we're going to look at the standard deviations next, because the empirical correlation, okay, not the theoretical one, this is the empirical one, okay, from a sample is going to be, and then you have the empirical covariance divided by the product of the empirical standard deviations, the uncorrected versions. You might remember that, so in accordance basically with its theoretical counterpart. Now, the empirical covariance was 9, and the product of the standard deviations are, I mean, respectively, the square root of the variances. So the variance of x is 100, its square root is going to be 10, so 10 will be the standard deviation of x, the empirical one, whereas the square root of 1.44 is, I think, 1.2. Okay, so 1.2 is going to be the standard deviation of y. So if you put these things together, you're going to get 0.75. If I did it correctly, 0.75 is relatively close to 1, so you could argue that the correlation is positive. That's for sure. Okay, you have a positive correlation, which is, let's say, kind of strong. Okay, we have to draw the line depending on basically the test. You know, if you test it at the high 5% level, but I think every statistician would argue that a correlation of 0.75 would be considered as significant. Keep in mind, guys, that these are exact values. So I was basically setting up these numbers in such a way that every measure is going to be, you know, exactly obtained. All right, it was a lot of work, to be honest, you know, so, but anyway, that's just my problem. Anyway, all right, so these are not approximations, these are exact values, keep that in mind. All right, now, regarding the ordinary least squares estimation, okay, which is by definition the minimum or the argument that minimizes the residual sum of squares. Regarding the ordinary least square estimator, you have basically the result, which is the slope. Now, you need to know the formula. You might remember this from statistics. I mean, I didn't ask you this, but have you done simple linear regressions in a previous statistical class? All right, okay, and you know what I'm talking about. So you have the covariance divided by the variance of the predictor. Now, okay, so the covariance is 9 and the variance of the predictor is 100, so you get 0.09. Now, what does that mean? That this means, and this is the interpretation of the slope, so sometimes going to ask you this, it's not on the slide, but you need to know this. So if x increases, okay, and then explicitly by 1, okay, so by 1 unit, okay, whatever the unit is, okay, if x, the predictor increases by 1 unit, then you can say that y is expected, okay, so given x, okay, that's going to referring to a conditional expectation, okay, that's not clear from this expression, but I'm referring to the conditional expectation, okay, so then y is expected to basically to increase by b hat, or that's what basically you would argue here, which is the estimator for b. Okay, so b hat is an estimator, guys. Okay, so this is basically the OLS estimation, and you're supposed to be familiar with that. So this is what you would say, okay, is expected to increase, okay, because that refers to a conditional expectation, okay. So given that x increases by 1, this is what it's going to be. This is the expectation, all right? So regarding conditional 1, it's not clear from this description, but this is the interpretation. So if you go 1 unit to the right, okay, then you need to go basically b units to the top to stay on the regression line, guys. You understand? And if you stay on the regression line reflects your expectations regarding, or basically your fitted values regarding the response, all right? So the response is expected to increase by b if x, or if the predictor increases by 1 unit. Does that make sense? Okay, so that's that. But is expected to. So if you say it does, it's not true. Okay? You understand what I'm saying? So just because, you know, you have, let's say you increase, I mean, you cannot see this here clearly, right? But it's not necessarily true. Okay? So it can be also here, You increase the predictor and the response goes down. It can happen. Keep that in mind. So, but it's expected to go up if the predictor increases. You understand what I'm saying? So, but it's not, but it doesn't mean that it always does. Okay? So this is going to be important, guys, when you submit the paper. Okay? So don't say the predictor, the response is going to increase. It's not true. You don't know. But it's expected to, at least, if the coefficient beta, B is positive, which is 0.09. All right? So in this case, if X increases by 1 unit, then the response is going to be expected to increase by 0.09 units. That's the interpretation. All right? So please keep that in mind when you submit a paper. When I give you an assignment, I will also do the correct interpretation. So I'm expecting you to interpret that correctly, accordingly. Okay, so watch the video if you're not sure. Okay, because it's not written on the slide, and that was on purpose, because I want you to pay attention to that. Now, regarding the intercept, okay, so this is the formula for the intercept. This comes from the minimization issue regarding the mean of the squared residuals. Okay, so you have the mean of y, which is basically the 3.6 minus b, which was 0.09, times the mean of x. Now this yields negative 3.15. So this is basically where the y-axis is hit by the regression line. You know that this is the intercept, all right? Achsenabschnitt, that's the German term. So then you can basically put the two together, and this is going to be the regression equation, okay? Keep in mind, I'm going to distinguish between y and y hat, because y hat are going to be the fitted values. These are called the fitted values. So, or you can say the expected values given x. Conditional, this refers to conditional expectations, believe it or not. I'm going to basically do that one. So, but again, I call this the fitted values. This is how you calculate them, okay, it's by using the regression line. And I'm going to calculate the fitted values for y. So this is what you'll see, okay? This is something that you don't have to, okay, but I'm going to do how to calculate the fitted values, okay? So these are going to be here. Then you need to put the predictors or the observations for the predictor into the regression line. So that's what you do, okay? So you take negative 3.15 plus 0.09 times 60, all right? So you have 60 here, basically substituted for x. Does it make sense? And then you take the fitted, you will get the fitted value of y, which I'm going to address. Okay, so that's what I'm basically do for every sample observation there is. Okay, so then you see basically how it will go, and that's that. Is it clear? All right, so is it clear how I would calculate the fitted values, guys? Okay, the computer does that, so you would not need to, but you need to understand how it's done. Simply, you take the sample for the predictors, and then you would put them into the regression line, and then you would get the fitted values for y, and I'm collecting those here. So this, you get a new sample regarding the fitted values of y, or the expected values. You can also say the expected values, or you can also say the explanatory parts of y, because the fitted values are the ones that can be explained by basically by the predictor. You understand what I'm saying? All right. So then you can also calculate the residuals. The residuals are going to be the responses minus the fitted values respectively. All right. So that's just the difference between the two. These are the residuals. So deviation from your expectation regarding it. All right. So then you simply take basically 2 minus 2.25, which is negative 0.25. Okay. So you were basically overestimating this part. All right, because the response was smaller than expected. So then, of course, its residual is going to be negative then. So if the residual is negative, then you were overestimating basically your response. But in this case, I mean, this is also going to be negative, but in the next case, it is positive. So then you were underestimating. So sometimes you're overestimating them. Sometimes you're underestimating them, depending on basically what you have. Because some points are above the regression line and some points are below the regression line, obviously. So this is basically how it would work. Does that make sense? All right, so these are going to be residuals. Again, residuals are differences of the, of the sample of the responses, right, minus the corresponding fitted values respectively. Does that make sense? And I'm going to analyze these samples, guys. So looking at basically from here and establishing statements accordingly. So I'm looking at the arithmetic means again. You don't need to do that again because the arithmetic mean of the response has been done already, but I'm going to, just for presentations, Okay, I'm going to present them. Anyway, I'm going to look at the arithmetic mean of the fitted values. And if you take the arithmetic mean of the fitted values, you need to sum them up and divide them by 5, which I did. Okay, so I'm going to do that again. And this is going to be the same. So this is something that you need to know, that the arithmetic mean of the response is going to be equal to the arithmetic mean of these fitted values. How come? Because the residuals have the mean 0. That's it. That's the reason. Okay, so all the time, if there is a constant inside within the regression, okay, which it is in general, why would I take the constant out? Then the mean of the residuals is going to be 0. So then this means that the values that basically I don't expect even themselves out. So again, sometimes you're above, sometimes you're below the regression equation. All right, basically an average, I mean, that's what it says, it would be 0. So that's that. This is always the case, guys, okay? If the regression has a constant in it, which it does most of the time. So let's say without loss of generality, I would take out the constant. Now, again, I could show that to you also formally, but I don't. So I wanted to have that basically just demonstrated, okay? But you need to know this. So you need to know at least some properties of the regression, and then you would also do that. Now, again, if the mean, or basically both means are the same, then the mean of the residuals must be 0. That's for sure, because the mean of the difference is the difference of the mean. You understand what I'm saying? So if you have basically, I mean, okay, so A minus B, and then you take the mean of the two, then the mean of the difference is going to be the difference of the mean. The expectation is a linear operator, and so is this the arithmetic mean, of course. Okay, so this is basically what would be. So the mean of the residuals, since the residuals are basically the differences between the observed and the expected value for the response, you'll have, I mean, if you take those, you'll find that the mean is going to be 0. Okay, so confirming that. This is something that I'm expecting you to know. So if I asked you guys, in 1 or 2 assignments, I do this occasionally, what is the mean of the basically of the residuals? Then people tend to calculate the residuals, and then, you know, you have rounding errors most of the time because these values are not exact. And then they're like, okay, this is very close to 0. No, that's wrong. Mean of the residuals is going to be 0 if there is a constant in it. And I'm expecting you to know this. Okay, so sometimes, again, I drop assignments where I'm addressing this issue. What's the mean of the residuals? And then you're like, okay, 0, period. Okay, you don't even look into that. Is it clear? So so I would like to warn you. Sometimes I basically do that one. Anyways, okay, so yeah, and so I'm going to summarize it over here. So the mean of the response for the sample of the response is going to be equal to the mean of its fitted values. All right, so again, I'm giving you basically both formulas for that. You can see over here. All right, so that's similar, except that the responses are replaced by the corresponding fitted values. All right, that should be clear. All right, so that's basically number 1. You can show this also formally, which I don't, so I skip it, but that's easy to see, by the way. So if you look at basically the equation, A hat is equal to y bar minus b hat times x bar. Okay, and if you rearrange that stuff, you're going to have the mean of basically the mean of y being equal to a plus b times x bar. And this expression, of course, equals the mean of the fitted values. Okay, so that's basically the proof for that statement. But I wanted to basically just demonstrating it. So you have, I mean, you have seen this in the sample confirming this, but this is also true in general, provided that the regression has a constant, which it has, okay, which I assume that it's going to be. Now, this means that the mean of the residuals are, again, and you see this over here, the differences between the observed values for the response and versus the fitted values. Okay, so you take basically the difference between the two and you subtract those, and then you'll find that this is going to be equal to 0 if the regression has a constant. So if there is, let's say, a, which is a constant inside. If you take the constant out, then it's not going to be true, okay? Because basically one regression line crossing the origin could not be fitted in such a way that the residuals would be equal. I mean, the mean of the residuals would be equal to 0 in general. But why would you take out the constant from the regression? I mean, technically nobody does that, so you could, but there is basically no need to do this. Anyway, so even if the constant is not significant, right, I keep it there. Anyways, is it clear? So that's something that I'm expecting you to know And sometimes I drop questions regarding assignments, you know, what would be and this and that. Anyways, okay, now the other issue I'm going to address is going to be the empirical variances. You don't need to address the empirical variances basically for the corresponding, for the response. We already had this mean of the squares, right? Minus the square of the mean. So you have the mean, this is the mean of the squares, and then minus the square of the mean. We did this already, so you don't need to consider that one. But I wanted to have that compared to the variance of the fitted values. Same approach, mean of the squares, you got that, right? So mean of the squares, here are the values, all right? And you take the square of each and then you put that into the sum. This is the mean of the squares minus the square of the mean. Now, guys, this is the mean of the square is, of course, you know, that you have the same mean. So again, keep in mind that the mean here for that one. So again, just writing it down. This is the mean of the response, all right? So this is 3.6, which is also equal to the mean of the fitted values. So I want you to remember that one, all right? So that's why I was not collecting basically the arithmetic means here from the fitted values, all right? Because we also know that the mean of the residuals will be 0 then. So that's that. Of course, the variance of the fitted values is smaller, usually, than the variance of the response or the sample for the response. How come? Because you don't have the residuals in there. Okay, so that's something that you would need to know. All right, so you take out the residuals. The residuals are basically the unexplained parts. And also keep in mind, this is going to be also important sometimes. So when you take, for example, the correlation between the predictor, or who can say, could be a question. What's going to be the correlation between the predictor and the fitted values? Keep in mind the fitted values are basically a linear transformation of the predictor. So if basically one sample is a linear transformation of the other, then the correlation is equal to either 1 or -1. And since basically B is positive, then the correlation between the predictor and the fitted values is going to be 1. If you don't believe it, then you can basically confirm it for yourself. Is it clear, guys? So sometimes I also drop questions like this. Okay, correlation between predictors and the fitted values is going to be either 1 or -1. Why? Because the fitted values are always a linear transformation of the predictors. You understand what I'm saying? So that's basically you need to be aware of. I could show you that one also, but I didn't consider that one. And basically doing that, if you want to consider, let's say, also the correlation between the predictors and the residuals, the correlation between predictors and residuals is 0, okay? Because the residuals constitute those parts basically of the response that you could not explain by the predictor. So by taking out the impact of the predictor from the response, you're left with basically those parts of the response that you could not explain by the predictor. So that has no impact on it, right? And then, of course, if there is no relationship or no linear relationship, because you have linear relationships here involved, the correlation between predictor and residuals are going to be 0. Is it clear, guys? So that's something that you need to understand here. All right, so let me repeat what I just said. The correlation between predictors and the fitted values is either 1 or -1, because the fitted values are always a linear transformation of the predictor. You understand what I'm saying? All the time, okay? And in addition, the correlation, maybe you could check that out if you like, okay? So these values are exact, so you can basically, you can look at that one. The correlation between predictors and the residuals are going to be, the empirical one, are going to be 0, okay? Because the residuals constitute those parts of the response that you could not explain by the predictors. Understand what I'm saying? That's it, okay? That's it. So this is basically it. You could confirm this if you basically want to check it out, but I didn't, but that's something that might be good to know. All right? Well, I will come back to that later on. Now, what about the variance of basically of the residuals? If you take the variance of the residuals, mean of the squares, right, minus the square of the mean. Why I have 0 square here? Because the mean of the residuals is 0 if you have a constant in the regression. So the mean of the squares from the residuals are going to be the empirical variance. You understand? So you take the sum of the squares, okay? And the sum of the squares are going to be called the residual sum of squares. So this is a very, I mean, I'm going to come back to that later on, but you'll see. The parentheses inside is the sum of the squared residuals, you see, divided by the sample size, yielding the mean of the squared residuals. And again, the mean of the squared residuals is equal to the empirical variance because the mean of the residuals is 0. So mean of the squares minus the square of the mean yields the mean of the squares. And this bracket, so inside the bracket, okay, is called the residual sum of squares. So RSS is going to be an important output. Sometimes you see this basically when you run a software program. This is going to be the sum, the mean of the squared residuals. All right, you need to basically to be aware of that, but I will come back to that later on. This is a very important one. Now, all right, so you see that this is 0.63. Now, if you compare these things with each other, you find that the variance of the response, or from the sample of the response, is going to be equal to the variance of the fitted values plus the variance of the residuals. So if you add the two, okay, you could basically add the two, you come up with basically that is being equal to the total variance. So the blue one is also called the total variance, okay? So you can simply say the total variance, then the variance of basically of the fitted values is called the explained variance, okay? And then explain, all right, or the explained variance, or the variance of the explained parts, and then you have the variance of the residuals. And then you simply say this is the residual variance. You understand what I'm saying? Okay, and this is basically the explained variance plus the residual variance equals the total variance. This is called the variance decomposition, by the way, which I'm going to address on the next slide. You understand this phenomenon, guys? Okay, so you decompose the variance. That has something to do with the law of total variance, because that is also, you know, you have an explained part and then you have the unexplained part. But again, this is what it would be. Okay, so again, this is the sum of the other two. You need to see this. Okay, so 0.81 plus 0.63 equals 1.44. This is not a coincidence, by the way. This is always true. Okay, so the total variance is always going to be the sum of the explained variance plus the residual variance. And I wanted to have that written down. So again, total variance on the left equals the variance of the fitted values plus the variance of the residuals. Empirical variances, by the way. Okay, uncorrected versions. All right, so that's also important. I basically explained them over here. Mean of the squares minus the square of the mean for each. This is the mean of the squares minus the square of the mean for that one as well. But you need to also remember, so when you look at that, basically, you need to remember that the mean of the, basically of the response, or a sample of the response, that one, I'm talking about that, or its square, basically is also equal to that one. All right, because the mean of the fitted values is equal to the mean of the response. Do you understand that, guys? All right, so that's basically what it would be. And then the mean of the residuals now, mean of the squares minus the square of the mean. The square of the mean is 0, of course. This is going to be the residual variance. All right, that is always true in every linear regression model. And based on that, we want to know what is going to be the ratio of the variance that we can explain, which I'm also going to address. Now, I'm also defining basically the sum of the squares, okay? So you see what is going to be. There are 3 of them, and that, of course, is equal to it. Now, if you want to have the sum of the squares, all you would do, okay, so ignore in the middle, all you would do if you want to get the residual sum of squares, you take the variance of the residuals and multiply it by the sample size. That's it. Because the variance actually is equal to the residual sum of squares divided by the sample size. So if you want to reverse it, you want to get the residual sum of squares, you multiply just simply the variance of the residuals by the sample size, and yielding basically the sum of the squared residuals. All right, and the residuals are going to be seen here. Now, the definition, okay, I didn't put this on the slide because this is more on an application. The definition of an OLS estimation, so which I'm basically addressing here. Okay, so A and B, which I call basically the parameter vector that I'm going to estimate, is the argument that minimizes basically the residual sum of squares with respect to A and B. All right, so this is basically the definition of an OLS estimator. You understand what I'm saying? Okay, so if you change that to be, let's say, a parameter vector, so I'm going to call this beta. Okay, so beta OLS in the multiple. Okay, I mean, for a multiple linear regression model in general, you have basically a minimization that you need to do. Now, residual sum of squares depending on basically on the parameter vector, and you choose the parameter vector in such a way that it minimizes the residual sum of squares. Is it understandable? So based on that, this is basically the definition of OLS estimation, by definition. But I didn't, again, so I didn't put this on the slide. You don't need to write this, by the way, so just for you to know where it's coming from. So again, I want to give you the context as well. Okay, so that's why I need these sum of squares. Now, this is called the total sum of squares, and this is the explained sum of squares. Again, explained sum of squares is going to be the sum of the squared differences between the fitted values and the corresponding mean. Now, keep in mind, this is not equal to the sum of the squares of the fitted values. So the total sum of, so the total sum of squares is not the sum of the squared observations, basically from the response or even for the fitted values. That's not the same. Okay, so that's not it. The total sum of squares is, by definition, the sum of the squared differences of each observation from the response to its arithmetic mean, or to the arithmetic mean of the sample. Is it clear, guys? And that's not equal to the sum of the squares. Got that? So pay attention to it, because that would be another sum of squares. All right? Okay, not the sum of squares of the sample observations, sum of squares from the squared deviations from each observation to the arithmetic mean of a sample. Is it clear? All right? So, of course, if the arithmetic mean is 0, then this is true. Here is an error on this slide. I just see it. Okay, so total sum of squares is equal to basically yi, which is the ith observation of the response, minus y bar. I will fix that one also. I apologize. Okay, but I was basically editing these slides from scratch, so there is a little error. But again, apart from that, it is correct. Anyways, okay, so yeah, and then the coefficient determination is the ratio of the variance that you can explain. So you simply take the explained variance divided by the total variance, okay? Or you simply take 1 minus the ratio of the variance that you could not explain, which is the residual variance, divided by the total variance. Since basically the variances are also directly proportional to the corresponding residual, to the corresponding sum of squares, you have the explained sum of squares divided by the total sum of squares, also yielding the coefficient determination, and then also 1 minus the residual sum of squares divided by the total sum of squares, also yielding the coefficient of determination. All right, guys, so again, keep in mind that the sum of squares are directly proportional to the variances, because if you multiply, let's say, a variance, okay, then by the sample size, you're going to get the corresponding sum of squares depending on what you have. So if it's a total sum of squares, then this is going to be the variance of the response. If it is the explained sum of squares, right, then this is going to be the variance basically of the fitted values, right? And if it's the residual sum of squares, I'm going to give you that one also, right? Then this is basically the variance of the residuals. All right, so that basically, depending on what you're looking at, but that's always going to be the same procedure. So again, these sum of squares are going to be always directly proportional to the corresponding variances. All right, that's not a big issue. All right, guys, so yeah, this is it. And then, yeah, so basically you could basically calculate this. Within a simple linear regression model, there's also the possibility to bypass that. If you want to basically get the coefficient determination, you simply take basically the explained variance and divide it by the total variance, which I did, okay, or 1 minus the unexplained part. Okay, so the ratio of the variance that you could not explain. If you can explain 60% of the variance of the response by using the predictors, then you cannot explain 40%. That does make sense. So this is the ratio. So just for you to understand, this is the ratio that you can explain, which is basically 0.5625, meaning that 52.65% of the variance of the response can be explained. Not the response itself, guys, the variance of it. You understand what I'm saying? So 56.25% can be explained, and 1 minus 52.65% cannot. So this is the ratio, whatever you got here, which is 43%, right? 43.75%. All right, so this is the ratio that you could not explain. Understand what I'm saying? 1 minus the ratio that you could not explain is also equal to the ratio that you can. All right? Is it clear as far as interpretation is concerned? So again, let me repeat, because this is something that is important. So exactly, and these are exact numbers, right? So 56.25% of the variance of the response can be explained. By what? By the explanatory variable, or basically by the predictors, okay? You understand what I'm saying? And basically the rest cannot, which is a relatively large part in this case. But that's just a side note here. This is the interpretation of the coefficient of variation, okay? Because this is the ratio of the explained variance on the total variance, guys. You understand what I'm saying? That's basically coefficient determination. This is one of the most important outputs when it comes to linear regression. And that's going to be also the case when you look at time series as well. All right? That's going to be important. Now, okay, so when it comes to coefficient determination, and then for a simple linear regression model only, so keep that in mind, for simple linear regression, what does that mean? Not because it's simple to calculate. Simple means only one explanatory variable. Understand what I'm saying? Only one. Okay? Actually, guys, just to be honest, the constant is also constitutes to be a predictor. Okay, so sometimes I use basically explanatory variables and predictors synonymously, but they aren't. Okay, because the constant is also part basically of the regression equation. But if there is just one explanatory variable, then you can bypass that whole thing, which is a little bit, more complicated, by simply squaring the correlation coefficient. So the square of the correlation coefficient is going to be equal to the coefficient determination. One assignment that I'm planning right now, maybe the next one, I'm not sure, from the theoretical perspective, is going to be about that. So you would need to address that issue. Okay, but I'm going to explain how. So don't worry. It's not going to be that difficult as you might see, because you're kind of confused by it, but don't worry. So again, I'm going to just show you, demonstrating you that this is the case. So an empirical correlation was 0.75. Keep in mind, this is the exact value, guys. Okay, so that's exact value, all right? So this is very accurate. It took a long time for me to conceptualize these numbers in such a way that they would work. So that was basically it. But anyways, okay, coefficient determination, if you square it, you will get that one. That's going to be not a surprise anymore. So this is 9 by 16, by the way. All right? And that's it. Okay? Now, I want to stop here. You have questions related to this? Yeah.
If you could go 2 slides up.
Yeah.
When we calculate R squared, we use the empirical variances.
Yeah.
And then another, I think, choose on 1 slide up.
Maybe that one? Yeah?
We have, this one exactly.
Yeah.
And then further up, we have that the explained sum of squares is the sample size times this empirical.
I mean, look, there is a direct relationship to it. So if you want to basically address it from here, you need to know that let's check out that one. Okay, so I want to give you that one. Maybe this is, confusing you. The variance of the, let's say, of the fitted values is equal to 1 by n times the explained sum of squares. Okay? And similarly, of course, the variance of the residuals, the empirical variance of the residuals is 1 by n times the residual sum of squares. And then you also have that the variance of the total, or the total variance, let's call it the total variance, which is the variance of the response, the empirical variance of the response, is 1 by n, so the sample times the total sum of squares. So if you replace basically these expressions that you see, okay, so let's say, take that one, for example, arbitrary, right? Take that, simply replace it by 1 by n times explained sum of squares. And do the same thing down there as well. Okay, so you would basically do the same thing here. You would find that 1 by n cancels out. So you're left with basically the explained sum of squares divided by the total sum of squares, at least at this part. And then you could also do that for residuals as well, similarly. You understand what I'm saying? So because they are directly proportional to each other. If that's a question that you want to ask. All right? Okay, but again, keep in mind, guys, these sum of squares don't refer to the sum of the squares from the sample observations, except for the residuals, because then the mean is 0. The sum of squares referring to the sum of the squared deviations of each observation to the arithmetic mean of a sample. Is this understandable? All right? Yeah, that's it. Okay, so that was it, guys. Okay, all right. I'm going to update the slides because I found some errors there. I apologize. We're going to see you tomorrow, and then we're going to talk about hypothesis testing among others. But that's going to be there is one question left. So.
I would like to ask about the assignments. If there will be also like partial points.
No.
Or...
Yeah.
Okay. So.
But I hope not. So I hope you're going to get the full score. You understand what I'm saying? I tried to conceptualize basically in such a way that you're going to get at least partial results, okay? But I need to penalize you sometimes here and there, okay? So you need to make sure that this works, you know, at least at the beginning, all right? Does that make sense? Okay? Yeah, okay, guys, so, okay, we're going to see you tomorrow, and tomorrow I'm going to talk about hypothesis testing among others, which I mentioned before. All right, that was it. Thanks. Take care. All right.